Hello everyone, can you see me? I just need some confirmation. Yes, you can say just yes or something so that I know that I'm live. Okay, evening, welcome. Okay, great. So let me start now. So today's our topic is like this, that let me show you the slide and then we can get. So from simple Sophie Germain to Indian and Romanian national Olympiad problems. Now, the little story is this, that this Sophie Germain identity is very simple. Of course, high schooler now, class 8 student knows it, but then it has got really lot of applications. So in today's lecture, I will try to develop some kind of reasoning behind it, and also its applications in particular forms. And we will end with some Olympiad problems. I will take Indian National Olympiad problem. Romanian was also similar, right? So you can try by yourself. So let's start now. So let me add the slide and then I'll show you the problem so that it will be good for you. You can see it and you can understand. See, this is the problem that was asked in 2010. I think 2010 or 2009. Just check it. That is just a matter of searching the Google one. Okay, so I mean, what happens that here this problem was asked in RMO. It's a good problem, but still not many people could do it. Not many students could do it. Reason was, of course, that they thought maybe it is tough or what, something like that. See, it was 10 years ago, not now. See, you can see the level of hardness, level of difficulty. Not now. It is now 2021. So that was really a charming problem of that time. So I will develop some little theory and then I will do problems. This I will do in the last. Others also are there to whet your appetite. Many more are there. Some conventional, some are and some are real hard. Okay. So now first let me add a page, and those people who are newcomers. Okay. So let me go and let me ask them, because we have to understand that they also might not know the identity itself first. So first is this one. Let me write. So first is that simple thing, a to the 4 plus 4 times b to the 4. This is the factorization. So what I do, we do the time honored technique of completing the square. So we write a squared plus 2b squared whole squared and minus 2 times a squared times 2b squared. Some of you might find it very elementary. Some of you, I apologize, because some of you might be well read, but then it's a YouTube class, and so I'm sure that many of my viewers are from class 7 and 8, the young kids, and so it is important to derive it once. It won't take much time, so please bear with me. I hope that's all right. Okay, so now this is this. So I'm writing like this. So let me write plus here, and then I will write here negative of 4a squared b squared, 4a squared b squared, and so you will get here a squared. This whole thing now becomes a squared plus 2b squared whole squared. And my only request is that please lend me your ears. You can chat, you can ask more questions also. But then I understand that please really just enjoy the lecture, sit calmly, and let the fun begin. Okay. So now this is 2ab whole squared. Okay. So now I can write this as a squared plus 2ab plus 2b squared and a squared minus 2ab plus 2b squared. The book, normal book stops at this point. I will not stop here. I would rewrite it again. So I will write like this, that see, I will use this in this form, that look at it, that it is first this one. I will write it as a minus b whole squared plus b squared and times a plus b squared plus b squared. Sometimes this representation, this form helps me to see things more clearly. It is like sum of 2 squares. See, it is like sum of 2 squares, right? Each product. Okay, and it is brief also, right? In particular, if I take AB to be positive, if I take AB positive, A and B positive, or non-negative both, then I can say that the second factor is greater than the first factor. You agree? Because b square is there, and a plus b, of course, things are positive. So a plus b, of course, will exceed a minus b, given all things are positive, not negative. Okay. So that can work, and anyway I can check always, right? This form will have its uses. So this is called, this is known as, what is known as Sophie Germain identity. Sophie Germain identity, or factorization. This is the name of this. Now, couple of thing here. Suppose you have got n to the 4 plus 1 over 4. This factorization, it is same thing, right? So what somebody has done, they have chosen b equal to 1 and moved 4 here, 1 by 4. Anything will work, right? So I can write this as n squared squared plus half squared plus 2 times n squared times half and minus 2 times n squared times half. So I get again time honored technique of completing the square. You complete the square, n squared plus half whole squared minus n whole squared, and so I get again difference of 2 squared, n squared minus n plus 1 over 2, and then n squared plus n plus 1 over 2. If you like to write 4 into the 4 plus 1, just multiply 4 throughout and you end up with the same different form, 2n squared minus 2n plus 1 and 2n squared plus 2n plus 1. I mean, you can play around with it, right? You can play around with it, you can love it in multiple ways, and identity remains the same. Now this identity is the source of so many beautiful Olympiad problems. Some are thinly veiled, some are heavily disguised, but all of them are lovely, interesting, and quite fun. And the beauty is that any high schooler like class 8 or 7, they can understand it. It's perfectly fine. It's like that nothing great you are doing here. We are just doing simple factorizations. That's why the title was that from simple Sophie Germain to like marvelous problem of Olympiads, Romanian, Indian, Hungarian, you name it, every country will propose somewhere or the other, or they might have proposed. Okay, let me move on to the first example that I will call the poster boy of our examples, because that is one you will find in every book and everything. That is this. It also came in RMO long back. Long back means maybe 20 years ago. It was good. Now it is a very simple one, but good for introduction. So they are saying find all primes of the form n to the 4 plus 4 to the n is non-negative integer. I mean that if n greater than or equal to 0, you are supposed to find that what numbers, if I keep putting the values for n, let's do some experiment, n0. So n0 will lead to, no, if you put 0, it will lead to just 4. No, it will lead to 4, 1, it will lead to 1. N equal to 1, it will lead to 5. N equal to 2 if you write 2. Then at 2 you see something strange happening. 16 plus 4 square, obviously prime, obviously composite. Then n equal to 3, you will find again 81 plus 4 to the 3 and all those things. You will still find that these all numbers are composite, right? N equal to 1 gives you prime 5, and n equal to 0, of course things are 0, so not interesting. So 4 0 1, so that is also 1. So 1 is, you know, 1 is neither prime nor composite, right? 1 is neither prime nor composite. 1 was actually banned out from both the clubs, right? Because it cannot be, because if you make 1 anything, then you will lose many properties, and then every theorem would have to be restructured, like prime number theorem, right? Those kind of thing. Okay. Now, so 1 is neither prime nor composite. That of course we know, neither prime and nor composite, and so it seems that n equal to 1 equal to 5. But then yes, in maths we need proof. No, we can't just say that n equal to 1 5 and so done, and we cannot say that we see the pattern, it continues, because who knows, pattern may break after maybe million numbered, we do not know, and that's why we need the proof. So the point is that I need a proof. So now I'll break it up in two cases. So let's take cases n equal to 2k. That looks a good case, k greater than or equal to 1. In these lectures, I will also tell you how to write the answer. It's very important, so that you don't fake solve it. You know, there is a term called fake solve. There is a term called fake solve that is referred to say that somebody who really think he solved it, but then alas, it was wrong. No, so that is referred to as fake solve. That you thought that you were doing the right thing, guy, but then alas, that was wrong. You were not graded for that, and then you came out crying, thinking that, oh, like I really did the work, but I don't think they rewarded me. Okay, so n equal to 2k. Now n equal to 2k, if you take k greater than or equal to 1, then it is plain that you have got even things, right? 2k to the 4 and then you have got 4 to the 2k, right? So it is even and even, k greater than equal to 1, and so this is even, and so it is composite, right? 2, of course, we know divides it, and so these numbers are not there, right? N equal to 2k. N equal to 1 we have dealt with, so I will now deal with n equal to 2k plus 1, and I will take k greater than equal to 1, right? Because k equal to 0 case is already done, 5. So I'm looking to find out that if numbers more than this are composite or not, or prime, 2k plus 1. We should be able to prove that no, right? So 2k plus 1. So for this I will write this as, this expression E is n to the 4. Please be very punctual and listen carefully. N to the 4. So I'll write n, I will just leave n to the 4, it does not interest me. Plus 4 to the this n, I want to write 2k plus 1, this n, 2k plus 1. So n to the 4, and I want to see, remember my form, I want to pull out a 4. I want to pull out a 4. If you remember, we did something. It must be somewhere here, or let's check where it is. Okay, it is here. I must pull out a 4. You see, there is 4 is there, 4. So a to the 4, I am happy, plus 4 times b to the 4. So I need to pull out a 4, and there is an opportunity to pull out a 4, because the moment I write this, I write 4 times 4 to the 2k, and this I need to write as a 4th power. So I write n to the 4 plus 4 times, and this I can write as 2 to the something. So 2 to the k to the 4. So I mean we are ready, and because k greater than equal to 1, and so this is greater than equal to 2 to the k, right? So I mean we have got a to the 4 plus 4 times b to the 4. Till now it is all right that we got something. Okay, now the moment we got this one, no, now we do not need. So now what I'll do, I'll write in this form. See, form was n to the 4, so I will, or just write a to the 4 plus 4b to the 4, and so this is your, don't write this whole thing, don't write this, don't write this, write directly this one. Of course in derivation you will do it, but you will write this one. Okay, so now no need to check discriminant. Okay, just okay, now it is a plain proof, simple proof. Now you write this as a minus, you write this as, that proof is also correct, you write this as a minus b whole squared and plus b squared and times a plus b whole squared plus b squared. I will have to change the slide maybe, so let me write again. So n to the 4 plus 4 times 2 to the k to the 4, I am writing this as a minus b squared plus b squared. This is not a trivial point, a plus b squared plus b squared. So now see what happens, that your a was n squared and your b was 2 to the k, your b is 2 to the k, this is b, 2 to the k, right? If b is 2 to the k, then I will do like this now, that if I write here, this is n square minus 2 to the k whole square, it does not interest me, and plus 2 to the k whole square, and again n square plus 2 to the k whole squared and plus 2 to the k whole squared. Now you see that this thing is greater than 1, right? In fact, k is not 0, k is greater than equal to 1. So this is greater than 1, which is important. So the whole thing exceeds 1, because anyway this is non-negative, right? Even it is much positive, but non-negative enough serves our purpose. So this is greater than 1 and this is greater than 1, right? So I mean it is very important, because this expression E you are writing as a product of two terms. An important part is that each of which exceeds 1, each of which, please note it, each of which exceeds 1. If you fail to show it, each of which exceeds 1, that's crucial, exceeds 1, then only you are saying it is composite, right? Otherwise maybe that, who knows, you are writing E equal to 1 times E, or you are writing E equal to E times 1. In that case, of course, E is not composite. It is a trivial factorization, trivial, right? And so this kind of thing you must be careful enough. You can shorten the argument by saying that because this number, because this one alpha and beta, because alpha less than beta, so if someone can show that the smaller factor exceeds 1, if you can show that a smaller factor exceeds 1, a smaller factor exceeds 1, you are done. Because larger, of course, will exceed 1 then. You have already said that which is larger, which is smaller. Is that all right? Okay, so let's wait, like some lag might be there. I don't know what kind of reason, but okay. So a smaller factor exceeds 1, then also it is fine, because larger, anyway larger will exceed 1 then. So that is the thing. So is the video okay now? Somebody is saying it is freezed, video is freezed, but now, can you see now? Maybe there is some lag or something. No lag, now it's all right. Okay, please bear with it. Sometime it may happen. I'm working on it so that it does not happen. Okay, so this is one example. Don't underestimate the power of simple and instructive examples. See, I will just write for the benefit of young kids: simple and instructive examples. Don't miss the power of it while you are reading some subject, because these are the ones that will really hammer home the point. They will drive the message. Other examples will just confuse you, right? So first of all, these kind of thing, that okay, this is the one thing and you got it. So this is one example. You should revisit to just see that you know what this Sophie Germain thing is. That is the thing for sure that you will know. So this is trivial example. So we got the conclusion that the only prime of this form is 5. So your answer is that the only prime that is of this form is 5, and no else, because other all are giving either 1, neither prime nor composite, and all composite, right? So this is not. So this is done. A very good example, although simple but quite instructive, as I told you, and not to be missed. This tells you many of the argument, which again goes like factorization should not be trivial. It's not that you are writing just E equal to something and you are saying that look, E is a product of two numbers and so E is composite. No, it must be a product of two numbers, each of which exceeds 1. Otherwise, what you have rendered is just trivial factorization. Trivial. I mean, you are just writing E equal to 1 times E or E times 1, and obviously it does not prove that E is composite. It just tells you that trivial thing, that A equal to A times 1. So beware of these things. Let's go to next one. Now this is really interesting. Now things get pretty interesting. See how good it looks. That there is expression in FMN, and you are saying that prove that if 2021 whole squared and 2023 whole squared, this is divisible by 2022 squared plus 1 squared. Quite daunting. Looks quite bad, right? Quite big, right? This kind of thing. But let's break it. That what happens? How Sophie Germain actually comes to our rescue. It helps us. So first let me simplify this. F of m comma n equals mn plus 4 whole squared and plus 4 times m minus n whole squared. Let's simplify this. This is pretty easy to simplify, but then see what comes out of it. That is m squared n squared plus 8mn plus 16 plus 4m squared minus 8mn plus 4n squared, right? So 8mn miraculously cancels, right? They arrange like that. It is cancelled. So far so good. And you get now m squared n squared plus 4 times m squared plus n squared plus 16, and wow, it factors. It really factors well. So it factors like m squared plus 4 and times n squared plus 4. That's all right. But see, we wanted something power 4. No, we did not want a squared. We want power of 4. But all right, don't despair. Here it is squared something, right? So now if you do that, if I write that now, f of and mn. So if I write f of a squared and b squared, m is a squared and n is b squared, where a is 2021 and b is 2023, some numbers, random numbers. So you will get here 2021, or a to the 4 plus 4 and b to the 4 plus 4, right? You will get this one. So we got at least we got at least Sophie Germain form, a to the 4 plus 4 times b to the 4 plus 4. Now it will be really good. What we can do here is that we can factorize again. So this is, I told you, this is a squared minus 2a plus 2 and a squared plus 2a plus 2. You are a master of it now. b squared minus 2b plus 2. But it is better to write it so that we again understand 2b plus 2. And further, as I told you, it makes good sense to write a minus 1 whole squared plus 1, a plus 1 squared plus 1. Similarly, b minus whole squared plus 1 and b plus 1 squared plus 1. We can write like this. Does that make sense? So we got this one. Okay, now let me turn the page and go to the next one. So if I go to the next one, it will be this way. That, see, now I will put these values 221. So let me copy it on the next page also, because it will be easy for you to view it. So I got f of 2021 squared and this one. So I got f of 2021 squared and 20. I got 2021 squared and 2023 squared. This as, look at it, this is 2021 4 plus 1 and 2023 4 plus 1. But now notice this thing, that here, notice this thing, that anything you take, either this will divide or this will divide, right? This will, or plus. So it means that what I have noticed is this, that if you take n to the 4 plus 4, then n minus 1 squared plus 1 will divide this, and also n plus 1 squared plus 1 will also divide this one. Both will divide because it's a product of these. So these for this one, these both divide it. So if you apply it on 2021, apply this one, because you need this one 20. So the question was that 20, this number, call it n. The question was that 2022 squared plus 1. Let's check. This one squared, this whole squared divides n. So one factor comes from here. See, notice this one. 2021 squared plus 1. So it means you can say here that you can apply this one, and you can say that 2022 squared plus 1, that divides 2021 4 plus 1. That's all right. Okay, and plus 4. This is plus 4 and plus 4. So this divides plus 4. And also you can say, using this one, using the green one, using this one, you can say by this one that 2023 is 1 less. I mean that 2022 squared plus 1 also divides 2023 squared plus 4. Combining them, we can say that product of these, so 2022 squared plus 1 whole squared, that divide the product of these two, and that is what was to be proved. So it's a good problem, just telling that, okay, this is one kind of thing that you can always do. I hope that is clear. So here I just reviewed this fact that n to the 4 plus 4, this is important, I box it, that n to the 4 plus 4 has got divisors of this type. So just, this is n minus 1, 1 less than n, it is 1 more than n. So it is a square plus 1 and a square plus 1, and then you are getting this answered. So this is all right. Okay. Let's go to next one. Okay, now see how simple this problem was. It was looking big, no? Because those who are doing it the first time, they might think that, okay, maybe this is like this one. Yeah, correct. You can generalize, correct. Mathematically yours, it is correct that you are saying. Okay, same thing I am saying, that we have generalized. We have said that this always divides whatever comes. Okay, so whatever comes, I mean that for not whatever comes, like there is some small thing is this, that if you take off into the 4 plus 4 type expression, this expression, then this has got two factors, either n minus 1, both of them, either this or n plus 1 square plus 1. So when you are taking 2021, you are applying this one, the second one, this is second and first, and when you are taking for 23, you are applying the first one. So of course both will divide, right? So that's clear. Okay, I mean that of course one can generalize it, and you must generalize also. My goal is to make it such that if any problem comes on Sophie Germain, then you should be in a position to attack it, right? That's what you must do. So I think all are clear. Okay, Sumit, Uttam, Jadugar, mathematically yours, all are okay, good. I hope you are enjoying it. Let's keep moving. That is going to be so much of fun. And then of course, okay, this is simple. This is again number 2 or something. Prove that this is the product of two positive integers whose difference is 2 to the 507. Now, if somebody did not know Sophie Germain, he can still do it, like a class 7 boy, right, or girl. So a class 7 student could do like this. He would say that, okay, I want mn such that mn equals 2 to the 2002 plus 1, and he will say that I want m minus n to be 2 to the 507. You can give it to your brothers and sisters, the younger ones, who will of course try it. So they will attempt that. Okay, let's see, mn product is this, mn, we want mn positive, we want mn to be positive integers we want positive, and we want difference to be this and product to be this. So they will be happy. They will say that, okay, so I mean that I can form m plus n whole squared is m minus n squared and plus 4mn. So he can write this as 2 to the 507 whole squared and plus 4 times 2 to the 2022 plus 1, and so this is 2 to the power 1014 and plus 2 to the power, this is 2022, so 2026 will come, and plus 4, like that it will come. Now what we can do? Can you think of something that now what we can do? That what we can think of now? Because this is one thing has come up. Any suggestion by you people? Be quick, then I can complete the argument. Any suggestion by you people? Any of the viewers out there, that how we can really calculate this now? We have already got this one. Oh wait, m plus n was 2022, correct? So this one, so 2026 plus this one. So what we can write now? Can you tell something? What we can write? Yes. Anyone? Because we are writing this way, let's check our work first. That 2022 plus 1 mn, so we're writing 4 mn, and we're writing minus the whole square. So 2 to the 1014 plus 2 to the 2024, rather it is 2024. It is 2024, not 6. So 2024 and plus 4. So what it means, like, can we complete the argument from here? That can we complete? So how can we complete it? Is there a way to complete it? Yes, there is a way. I can write here 2 to the power 1012 whole squared, this term, plus 2 times 2 to the 1012 times 2 and plus 2 squared. See this thing. Again, time honored technique of completing the square. So 2 to the 1012 and plus 2 whole squared. So it turns out that this is a perfect square, right? This turns out this is a perfect square. And so if it is a perfect square, then we have got m plus n, because positive integer I can write m plus n is 2 to the 1012 and plus 2. This is equation third, say, and this let's number this as 2, 1 already used. So I mean I can just add them. So if I add it up, I get here, I get that 2m, I get 2m is 2 to the 1012 plus 2 plus 2 to the 507 plus 2 to the 507. Everything divides by 2, and so I can write 2 as m as 2 to the 1011 and plus 1 and plus 2 to the 506. And so this is one of the thing that we can get this one. Similarly, I can get n also. So it is done by the basic method that the people know that, okay, I can always write. Is that clear? Is that clear that we can get this one, mn? But let me do it a different way, and that's what we will bring to picture this one. That will bring to picture the identity, which will tell me directly that what we can do. So let us again take this one, 2022 plus 1. So let me go to the next page. Any doubt till here? Anything you want to ask? Any viewer can ask something if he wants to ask something. I have already given the motivation behind it, that this is how a class 8 student or a class 1 student who is a bright kid and knows some kind of factor, he can do like this. He will of course form this one. This is known, m plus n squared, m minus n squared plus 4mn, and he will try to calculate mn from there. He will be successful. But a good approach, now a good approach is like this, or rather one that fits into this chapter the way we are doing. So 2 to the 2 plus 1, lot many 2's. So 2 to the 2022 plus 1, this expression E, this I want to write as, I will write 2 squared, I mean I can write directly 4, and so 2 to the 2020 plus 1, so I mean 4 times 2 to the 20 plus 1, and so again I write 4 times 2 to the, and then I can take out 4 from here, so 505 to the 4 plus 1. So this reminds me of the form 4n to the 4 plus 1. So E is this form, 4n to the 4 plus 1. Now that's good enough, because this we know that this is 2n squared minus 2n plus 1 and 2n squared plus 2n plus 1. So I can still complete it, but I just need to prove something else, that I need to prove just that difference is something else. I need to prove that product integers which difference is this. So I need not calculate them separately. I know they're integers, but then let's see what we get, just to give you a feeling. 2 into n square, so n is 2 to the 505, so I'll get 2 to the 1010 minus 2 to the 506 plus 1, and here 2 times 2 to the 1010 minus plus 2 to the 506 and plus 1. So I can write 2 to the 1011 minus 2 to the 506 plus 1 and 2 to the 1011 plus 2 to the 506 in plus 1. So I mean we have displayed these two integers, positive integers, these two product of integers. See, they said right product of two positive integers, and whose difference, so difference means larger one is smaller. So if I take the difference, these all will cancel, only these two will remain. So difference will be 2 times, so this difference will be 2 times 2 to the 506, and so we get 2 to the 507. In fact, I need not have done this. I could have stopped here also. I could have stopped here also, here. I could have said that, okay, they're of course integers. They are of course integers, and they are of course integers, and then so they're of course integers. They're of course integers, and then the difference here is just 4n, and with n equals 2 to the 506, I can write 2 to the 505. So I mean 2a squared and 2 to the 505. So that gives you 2 to the 507, and that is your answer, that this can be written. So they wrote that, okay, this is to be proved. So correct. It was an easy one, correct. Yes, it was an easy one and really interesting. Okay, so this is the kind of thing that this is happening. Let me show you again. See, the problem, once you get to the right tool, then of course problems will seem easy. So I told you two methods. This is the method favored by the high schoolers, typically class 8 or 7, who did not have their brush still with this kind of problems, or say they are not into Olympiads, so they may not know this, but still they have got their mind open and they can try like this. This is first method, first solution, which is pretty basic, and nobody can complain that they didn't get it. They will of course get it. Other thing is that this tells you that okay, this is second solution, and that uses as its setting Sophie Germain identity, very famous. And see, before we know we know the answer. So that is this, and we can stop here also, that we can take the difference and this will be answered. Okay, let me move on to the more challenging stuff. I'm trying to build the momentum so that anybody who is following this, that's the idea of these lectures, anyone who follows it devotedly, religiously, he will find that okay, these all things he can get, and of course he can progress. Next, so to prove that these x, y, g, w, you have to prove these numbers, that these numbers are solutions of this equation. X squared plus 1, y squared plus 1, g squared plus 1 is w squared. This we have to prove that these are solutions. So how will you do it? This looks to be little this one, but with this practice we can do. Uttam boss, I will give you the next time, because this is a scheduled class, so there is a schedule to be followed, but of course you are welcome. Okay, so just think about it for a moment, that this looks like that okay, how but it actually verification, so of course you will find not too tough, you find ultimately easier. So how we can do it? So we can do like this. Now see, this is not Sophie Germain, but see, look at w. What is w? 8 into the 4 plus 2, right? So that is 8 into the 4 plus 2. The moment you write 8 into the 4 plus 2 and you write whole squared, something good happens. Something good happens, right? Because you get here 2 will come out, so 2 is coming out, so all right, this is 4, and 4 into the 4 plus 1 whole squared. So you have got again Sophie Germain. You have got Sophie Germain form, right? So what I can do is that I can write 4 times 4 into the 4 plus 1, and again 4 into the 4 plus 1. These two are all right. This you don't disturb, this you leave, this is because I need some kind of, this you leave. This I can play with, So I can write this as 4 times. This is little tricky, this is not so straight. After Sophie Germain, you still have to do some work. Okay, so it is 4 times this I can write first. So this is 2n squared minus 2n plus 1 and 2n squared plus 2n plus 1, and times this I will not disturb, this let it carry like this, 4, this one. Now any suggestion what to do with this 4? What to do this with this form? 4 times something. 4 times something you have to write. So what we can do? Any suggestion? Okay, so I have one idea up my sleeve. This 4, what I can do is that I can take 1, 2 here, 1, 2 here, consume here, and 1, 2 here. So bring 2 and 2 here. So I write 4n squared minus 4n and plus 2, and distribute 2 here also. So that is 4n squared and 4n plus 2, and times 4 into the 4 plus 1. Now we are in good shape. This happens to be a perfect square plus something, right? So this is 2n minus 1 whole squared plus 1. Good, we love it. 2n plus 1 whole squared plus 1, that's also all right. And this is I can write as 2n squared squared plus 1, right? So if I write in order, I can rewrite this as first will be this one. So I can write 2n minus 1 whole squared plus 1 times 2n squared plus 1 and times 2n plus 1 squared plus 1. You see, these are your x, y, and g. You started with w, you started with w square. Now, by the time you reach here, you have got your x, y, and g. You have got x squared plus 1, you have got y squared plus 1, and you also have got g squared plus 1. So you have got all these numbers, and then you will multiply with 2 in both a small power brackets. Correct. So that's what I did. Good suggestion by viewers. So I got like this. So this is what we will do. So is that clear? This was really interesting because you have to do something. Still we are on Cauchy Schwarz or on Sophie Germain. Okay, next. Let me go to the next one. Let m and n be odd integers. Prove that m squared n squared minus 4 squared plus 4 times this ends in 1 or 5. So it either ends in 1 or it ends in 5. Either of them. Means it concerns last digit. It concerns last digit. So let me see if some viewer is ready to apply and he is able to try. He wants to try out the ideas. Something similar, if I comment, something similar we met already with m and n, albeit minus and plus, but that argument can be again tweaked. See, we have got a deja vu of the form, like mn plus 4 whole squared plus 4 times m minus n whole squared, right? So this form is there for m minus n whole squared. So pretty much simple, mn plus 4, and this is also, this is mn plus 4, one is minus, one is plus, and m squared n square, you saw we wanted it there also. So first thing, that let me write it as e and try to expand it. Let's see what we get by expansion. So you're getting m squared n squared minus 4 squared plus 4 times m squared plus n squared squared. So you get m to the 4 n to the 4 minus 8 m squared n squared plus 16 plus, now here you get 4 m to the 4 plus 8 m squared n squared plus 4 n to the 4. So these two terms cancels, and so whatever you're left with is this one. Yes, many of the viewers have given correct answer. Good going. This plus 4 m to the 4 plus n to the 4 plus 16, and so it factors m to the 4 plus 4 and n to the 4 plus 4. It factors like this. Okay, once it factors like this, it is good for now the form of Sophie Germain, right? Sophie Germain form. But then now you need to look at these things, that okay, how you can prove that it ends in 1 or 5. For that you may take cases, because of course 1 and 5 are there. So we can take some cases. Like, can someone suggest what cases we can take? Like m and this is m and n. So what cases we can suggest? So basically we have to deal with this kind of thing. Deal with the form of that. How does k to the 4 plus 4? No, this one. Suppose this is p. So this last digit you deal with, this last digit, k to the 4 plus 4. So how do you write that? K to the 4 plus 4. This I want. So I can get something like this. That I can have k as this kind of thing. See, let's take k as modulo 5. Modulo 5 means I take k is 5q or 5q plus 1 or 2 or like that. So if you take k is 5q, right? So, or say you can k is 5q, right? Or someone can write that congruent to 5, something, anything you can write, k is 5q. So if this you write k is 5q, then you see power of 5 will come, right? If q is not even. If q is even, then of course not there, 4 can come. Okay, so if q is odd, so if q is odd and k is 5q, then you will know that k to the 4 plus 4 that will end in 5 plus 4, so that will end in 9. So if k is 5q, that will end in 9, right? and if k is 5 cube plus minus 1, 5 cube plus minus 2, this kind of thing, then of course you can find again k to the power 4, and what will end in now? 5 cube plus 1 is there, right? K4 is there, so you will see that it will end in 1 plus 4, that it will end in 5. It will end in 5. Is that clear? Yeah, you can take 135, all cases will come correct. That also is correct. Jyotisman, good suggestion that you can have the viewer. Jyotisman is very good. That of course it boils down to just taking cases. So it's just that you have to be careful that not to leave cases. So you have to be careful that not to leave cases. Not to leave cases. So if you take that also, it will be covered, correct? So I mean that once you do that, you will find 5. Now there are numbers of this form, right? So it means that either it will end in 9 into 9, because this may end in 9, this may end in 9, or 9 into 5, or so either this will end in 9 and 9 first, or 9 and 5, or 5 and 5, I think. So in all these cases we will find that the last digit, it will end in 1 and 4. So it will be, because 1 will come from here, like modulo 10 maybe. This is 5 and this is also 5. So it ends, so this E ends in 1 or 5. So that's what the conclusion is, that they said that prove that odd integers then ends in either 1 or 5. So we have done, because odd, that's why we are doing these cases. So is that clear? They only said that it is odd integers and prove that it ends in 1 or 5. So I mean it's pretty case work, that after a while you have to do the case work and you can get to it, that okay, this case work works. I hope this is clear. And then let me write as a lemma, separate lemma, this one, that because we met it twice, so I will just write, see, just I will write combine those two, because for future use people can keep it in their notebook, and that's what a good solver is, that you have to. So say this one, mn plus 4 whole squared. So I'll write both together, mn plus 4 and this one. So mn plus 4, so one was this, that mn plus 4. So let me just add. So these two results you should write, mn plus 4 squared and plus m minus 1 squared 4, this one, and other was mn minus 4 whole squared plus this. See, other last example of this kind, last was of this kind, m minus 4, it is just take mn minus 4. So if you do this one, then you understand, you will get ms square plus 4 and n square plus 4, because cross term, mn term will cancel, 8mn and negative 8mn. If you do this one, again same thing, this one, because this is, you will get this one, so you'll get ms square plus 4 n square plus 4. Just check it, because you should get ms square n square plus 8mn cancels, and plus 4m square plus 4n square and 16. So you will get this one. The way we got, if you check it, here we got already this one, this we got right now, and in previous also we had got this one. See, if you check, carefully check, this 4 times this one, so we get that one, m minus 1 squared, m square plus 4, n square plus 4. So 1 plus 1 minus, both are okay. So these things help you to see the general pattern. So both of them you should write as a lemma, as a separate thing. Okay, so these lemmas will be helpful. These lemmas helpful, so that when you take the exam, when you write your Olympiad exam or any exam, then these are at the back of your mind, and so your calculation becomes simple, and you are already aware that what you have to really do. So this we can do. Okay, let's move on to the next one. What about this one? This looks quite daunting, quite tough. Let the sequence, there is a typo, it should be xn, so please correct that, xn yn, and here instead of 2 it should be n minus 1. It should be n minus 1. So that's a small typo, you can see and you can check here. that what is happening. Let's see how it works. For that I may have to teach you something. Some people might not know this recurrence. Some people might not know this recurrence. Yes. One is this one. This recurrence is there, and then you have to use that how you will go. May I drop a hint that you might need what is known as mathematical induction. All of you might not be aware of that, so I will take a detour to teach you little thing. Mathematical induction you might need. Induction to prove some kind of relation. Otherwise, you do not know that how you will get this one. It does not look like Sophie Germain right now, but it will become. After a while, it will become like Sophie Germain. So how do we do it? How do you get that? The idea usually is same. Okay, anyone? Anything? I may wait for a minute so that somebody can tell if they feel like that they can do it. This also is a clue: x13 and x2 y12. And this recurrence occurs in a famous equation. Where you have you have got the answer by recurrence, and then you are getting it. True for n equal to 1 and take true. Nakul is writing, a viewer, that previous one was Lagrange identity, all right, but not so. It is much deeper. Okay, so let me tell you first what we mean by induction. What happens sometime that there is this is for the benefit of younger people who might not know in all rigor. So suppose there is an expression called P of n. P of n is a statement depending upon n. So Pn is a statement depending upon n. Okay, now what happens that suppose base case, there is something called base case. That is suppose n equal to 1. It may be n equal to n naught also, any base case, or n equal to 0 also. So there is some base case, right? N equal to n naught. Now what you are telling is this, that if this is true, if Pn holds for some value, say n, or pk holds n. So if Pn holds for n, and we can prove, means assume, we can prove that Pn plus 1 is satisfied, then by induction it follows that this is true. I repeat, there is a statement Pn that depends on n, non-negative integer or something. Now base case can be n equal to 1 or n equal to n naught, anything you need, that's a problem given. So if we assume that Pn is valid, Pn is true for all this one, Pn is true for all, then we can say, not really in GP, so that we can say that P of n plus 1 is satisfied. Suppose we can prove that, then we will say that by induction principle it is true for all n. Okay, this is the thing. It is called one type of induction. There is something called, this is called sometimes weak induction, or there is something called a strong induction. We may need one form or the other many times. Other form is this. Other form is this strong induction, that now you are saying that Pn is true. Pn is true for n equal to n naught, say. true, and then you are saying that no, that's not for here. A strong induction we are doing. So Pn is true for n less than n naught, some value, n less than n naught, or n less than, or say Pn is true for all. You can write a value. Now running variable is k. Pn is true for all k less than n, true for all k less than 1, less than n. And using this, if you can imply that Pn is true for pk plus 1, correct, means pk plus 1 is true for, say we say just k plus 1. Pn is true for, suppose you say that Pn is true for k plus 1, that is pk plus 1 is true, then by mathematical induction it follows that Pn is true for all n, for all values of n. Does that make clear? This is called strong induction. Strong. It looks like that you are demanding here much more. It looks like we are demanding here much more, but it's not so. In fact, both forms has been shown to be equivalent. In fact, both form have been shown to be equivalent as it should be. But it is called a strong induction is called weak. A strong, why? Because it seems like that we are demanding too much. We are demanding not only just immediate one, but we are demanding all. Means we are doing P1, P2, P3, all. Suppose P18 we want to prove 19. So we are saying that give me anything that from P1 to P18 all are true first. And then we will look for the testing of P19. But weak form is nothing like that. We only need P18, and then from there we conclude P19 is true or not. Okay, so how do you apply this now? So thanks Puskar, please stay connected, and nice that you are attending all my classes. It will keep coming. Okay, now see, this is induction proof, so this will be of course new to many people. Now see, here I will claim something. My claim. Let me write first. Let me write xn first. It's very tricky problem. Very tricky. So xn is induction. I just briefly told for the benefit of viewers. Xn is 3 xn minus 1 and plus 4yn minus 1. So this is 4yn minus 1 and yn 2xn minus 1 plus 3yn minus 1, right? This is xn and yn. Now my claim is this. X1 is 3, y1 is 2. This is the basic condition given, right? Now see my claim. Can you see what claim is there? It's a tough one. Does not look like, right? It looks like simple, but it's a double recurrence, right? Recurrence for xn depends on y. And you need not solve for recurrence also. You need not solve for that. Okay. So actually this is this one that you try to find out. It arises in a famous equation of some solution of famous equation, very famous equation. Very famous. The moment I write, you will know. My claim is xn is, yes, it can be asked. Xn is square minus, because this is, you have to guess that what can satisfy. Xn is square minus 2yn square equal to 1. This is my claim. Xn is squared minus 2yn square equal to 1. Of course, we need not know the theory of this, correct? So no, not the claim. The claim is this: xn is squared minus 2 times y squared equal to 1. This is what we know. This is what we can do. Equal to 1. Now let's prove it. Base case. Let's prove it. Let's take the fun. Base case is not Fibonacci. It's not Fibonacci. Actually, it spells equation, if you know what I mean. But no knowledge is required. It is just disguised in this form. No need to require that whether you know solution or not. But then you can say, okay, correct. So mathematically yours. So of course, so it is like that you are just writing this one. So correct only. It is actually some other equation. Good. So what I will do is this, that I will prove this. So base case is x1 square minus 2y1 square, and that is 3 square minus 2 into 2 square, that is of course 1. So base case is proved. Assume that this is 1. Assume Pn to be true. Induction. Assume Pn to be true. I am also teaching you how to write. Assume Pn to be true. Now basis is there. Now inductive step. Now inductive step. Inductive step means that you have you know that xn square minus this equal to 1. Use this to prove, implies prove that xn plus 1 whole squared minus 2y whole square equal to 1. This you want to put, this is your goal, objective, and this we can do. So next page is, I will write like this only. So it is xn plus 1 whole squared minus 2 times this is equal to, now see, remember your recurrence xn plus 1, just go back. Xn plus 1 is 3, xn minus 1 plus 4, 3, 4 and 2, 3. So this is 3 xn minus 1 plus 4 y minus 1 whole squared minus 2 times, and this was 2xn minus 1 plus 3yn minus 1. Let's check it. It was 4 3 and 3 2, 4 3 and 2 3, right? 3 4 and 2 3. So 3 4 and 2 3. Now if I write it, it will come 9 xn minus 1 whole squared plus 24 xn minus 1 yn minus 1 plus 16 y minus 1 whole squared minus 2 times this is 4 xn minus 1 whole squared plus this is 12 xn minus 1 yn minus 1 and plus 9 yn minus 1 whole squared plus 9 yn minus 1 whole squared plus 9 whole squared. Now you see, now things cancels, right? This 9, yeah, correct. Now it is this one. Now this is 9 and this is 2 4 8, so it is xn minus 1 whole squared, right? I mean I should have written xn here, not all. So we can write this one, that is, it is all xn, right? So we can write here, this I can change, and this I can write xn squared, or you can keep everything same. So xn squared minus 1 squared, so you can say this one. So now this is, see, 9 minus 8, so this is 9 xn squared minus 8 x minus 1 squared, this comes, and see this is 16 and minus 18 y minus 1 whole square, right? 24 goes off, 12 times 2. So you are getting here xn minus 1 squared minus 2 times squared. So you have proved, this is 2. So you have proved now that this is indeed true, that this is true. So we got here that xn squared minus 2y1 square equal to 1. We proved by mathematical induction, by all induction we proved that by induction it is true. We proved that. Is it all right? That induction idea is all right? Are you aware with that? This is a good one. Xn squared minus 2y1 squared equal to 1. This we proved. Let me review. For the benefit of our viewer, let me review once. Any question till here? Anything you want to ask? You like to ask anything? Okay. So let me just show you. It's a really tricky question. The question was that the sequence xn and yn be defined by the recurrence. So some recurrence given. It is double recurrence. I mean xn depend on xn minus 1 y minus 1, and yn in turns depend on xn minus 1 3n minus 1. You can also write in matrix form. I will show later. Prove that sequence zn, an element of n non-negative integers, this one, defined by recurrence relation, does not contain any prime numbers. Means there are no prime numbers, right? So this is what you have to prove. So now what we did, that first of all we guessed the pattern. We guessed that actually what is this sequence? First step was decoding the sequence. How to decode the sequence? So decoding the sequence, the first step. Once we decoded the sequence, and we thought that okay, so that brought to mind Pell sequence for many of you, right? But that is not required. So now we got this one. So we are writing here xn squared. So our claim is this xn squared minus 2 times yn squared equal to 1. We proved this claim using this thing. See, just see how you proved it. We first get the base case, then we assume the inductive step. Inductive step means we assume this one and prove this one. Rather, I assumed xn minus 1 and y minus 1 and assumed for the next variable. You can do anything. I just got mixed up my n and n plus 1. So using this, we proved this. So we got this one 1. So that is done 1. Now the real part, that it is saying that sequence 1 plus gn is gn, this one, this has got all the does not contain any prime. So I'll write now very cleverly. I'll write zn is 1 plus, and this is 4. Let me check, it is 4 or 2. It is 4. 1 plus 4. So 1 plus 4 xn squared y1 squared. They are saying that this contains prime. So how can we write this now? See, use this one, the beautiful thing, xn squared minus 2y1 whole squared and squared, right? You write like this. You wrote like this, that xn squared minus 2y1 squared. Just check it first that you got something similar. So this is 1. This is 1. Now after this, what I can do, that I can, of course, this is negative 4 and plus 4. So instead of cancelling, I will write here this way, that, or we can use now this one. We can use now the Sophie Germain form. So I can write xn to the 4 and plus 4 yn to the 4. This we can write. This we will get this one, because this 4 will cancel, and so you will get here xn squared plus 2xn yn plus 2yn squared times xn squared minus 2xn yn plus 2yn squared, and that is equal to, you can write in this form also better, xn plus yn whole squared plus yn squared and xn minus yn whole squared plus yn squared. You see, given yn greater than equal to 1, so you see this all number will keep increasing. So you know this will have infinitely many. This one does not contain any prime. They're saying does not contain any. Same question that we started, n to the 4 plus 4, because now we can say that this one, that this is product of two factors, and you see the part is that this is always greater than 1, right? So both factors are greater than 1. That is also one thing to be noted and written, that if it is like this, and so we can say that Zn contains only composite numbers. No, they are saying does not contain any prime numbers, right? Does not contain any prime number, does not contain any prime numbers, no prime numbers. That is true. It's just like n to the 4 plus 4, which is containing 1. So it does not contain any prime number. That you can check here. Is that all right? Is the idea clear? Okay. This is a tricky problem. Okay, now let's see this problem. Of course, I will try to do the other one, but let's see this also. 3 to the 4 to the 5 and this one. This is Romanian 2009, and that was the first question that I told you. It was National Olympiad, regional, I think, in India, 2009. Let us do that question. Yeah, it's this. This can be written as a product of two positive integers, each of which is larger than 2009 to the 182. So let me do this one small, and then we check that what we can do. The first thing to notice that if I write this as e, then you've got 3 to the 2008 plus 4 to the 2009. You cannot miss this thing, that they are given to you multiple of 4 for some reason, and this is multiple of 4 plus 1. This is multiple of 4, not without any reason, right? So now, yes, mathematically your comment may be valid in that context. Now I can write this as this is 4. See how the problem was made, how it was created. That gives you another story. So 3 to the power 502 to the 4 plus 4 times 4 to the 2008. You pull out a 4 because you need a to the 4 plus 4b to the 4. So now this is 3 to the 502 whole to the 4 plus 4 times. Now 4 to the 208. I win 4b4, right? b4 I need. So I can write that. I can write 4 to the 502 to the 4. This I can write, right? 4 to the power 502 to the 4 I can write. So this is actually the form. Now it seems like that we are getting where it all coming from. So a to the 4 plus 4b to the 4. This came rightly, this one. Now next step can be little easy, like if you understand. So what we can do? Yeah, so now it may seem simple to you, because see, you was asked 2010, now it is 2021. Everybody has now read more and more, and so it may seem somehow simple, but imagine those times. They were so advanced, Olympiad is so advanced that 2010 they asked this question. If I borrow a phrase, I can say that, okay, like much water has flowed since then, right? But then, of course, now it is. But then the other part is all right. The second part also is there, that you have to prove larger than. So hold on, you have to prove larger than this also, larger than this also to prove. So that is also one thing. Okay, let's go. So 3 to 4 502 plus 4 to 502. So I write a to the 4 plus 4 times b to the 4, because I will not waste my time writing this one. So we can write this as a squared plus 2ab plus 2b squared, and a square minus 2a plus 2a square. See, because they are saying each of which is larger, each of which. So better you prove that the smaller factor exceeds this one, then larger automatically exceeds. That's the, we can save some time. So this is a smaller factor. You write this as a minus b. We write this as a minus b whole squared and plus b squared, and we write this as a plus b squared plus b squared. See, they gave both factors. This is smaller, this is a smaller factor, this is larger factor. So each of which is larger than this. So I will prove that a smaller, in fact, yeah, correct, that you will have to, this one, that you will have to inequality. Yes, inequality is like very weak, of course, but don't worry, a minus b square, right? So we will prove that a smaller factor exceeds that number, a smaller factor. So a smaller factor means this one. So let me turn the page and let me write it first here. So a minus b, that is 3 to the 502 minus 4 to the 502 whole squared and plus 4 to the 1004. This is the smaller factor, the smaller factor, which I will prove that it exceeds this one. Let me turn the page now. See, this is always positive, right? So I need to take care of very small bound, crude bound. Crude bound does the work, as somebody observed. So this is greater than 0, and so this I will write. So a smaller factor exceeds this one. Let me write on the next page. So a smaller factor, larger than, of course, will a smaller factor greater than, and then just check again, 4 to the 1004. It is 4 to the 1004. That is 2 to the 2008. This is, and I have to compare that. I have to prove that 2009 to 182. We have to prove that this is, so this is a question mark because you have to prove it now. So prove, it is not done still, right? So 2009 to the 182. Let me check, it is same thing. Yeah, this they want some quirky number 182 or something. Now the trick is that compare 2 with some other power, right? So powers of 2. So you see that if you write powers of 2, then people know normally 210 people know. 2 to the 10 is well known. 1024. Then 211 is 2048, right? This one. From here, can you see how you can finish quickly? It is much weak, as somebody observed. It is much weaker. It is much weaker problem, but still it holds water. It still is good enough. Okay, so what I do that I say that okay, this is 211 is there, and 2009. So if I aim that if I can prove if I can prove it's like backtracking. If I can prove that 2 to the 2002 exceeds 2048 to the 182, then we are done, because this will obviously exceed 2009 to the 182. Means you are getting the closest power of 2. The closest power of 2 is 2018. Yes, Nakul, I think that works. So closest power of 2 to this is this one, 2048. So that is our good bet. So I will write now again this. So we'll start this and write that 2 to the 2008, this is greater than 2 to the 2002, and this is 2 to the power 2002. Now this is 11 times 182, right? We had to write this 11 times 182. Just check it, 11 times 182. So now this is this, correct? And so this is equal to 2 to the 11 to the 182, and so this is 2048 to the 182. So we have proved. So what we have done is 2 to the 2008 exceeds 2048 to 182, and this in turn is much larger. See, it is much larger. It is much larger than 2009. It is much larger. That was the 1 year before the exam. 2001 to the 182 means it is very weak. This was very weak, not very strong inequality, but still the idea was not this. Idea was just to compare. So I think both of many viewers have given good solution, correct solution. So it is good. Yes, it is really good that people are enjoying and people have written so many comments, and then it is also that they know what to proceed from now. So I mean that this kind of thing makes you really simple. Okay, so let me go to the last one, and let's this will be your homework. Okay, you will, as mathematicians say, that you have to get your hands dirty if you want to understand things. I mean, you have to take your pen, paper, and then you have to write. So Romanian Olympiad we'll just look at for a while. Any questions here? This looks like a good makeup, but deep down it is again Sophie Germain. Say this one looks nice, right? So this expression E is 3 to the 4 to the 5 plus 4 to the 5 to the 6. So it looks like tower of powers, right? I like to call it as tower of powers. Always it looks fascinating. Again, we are looking for I'm looking for my a to the 4 plus 4 before, so I'm looking for a 4. So this I just leave. So I write 3 to the power 4 to the 5, and then we can write here that, see, I want to write some 4, correct? I want to write some 4. So see, if you have got a to the something and 4 is there, I can write 3 times 4 into 4 to the 5 minus 1, right? And 4 into 4 to the 5 6 minus 1, right? This is also much good. This is better. Okay, so this is 3 times 4. So I can write 3 to the 4 to the 4 and whole to the 4. I hope it's all right, because a to the a to the 4 n to the something. So again power gets multiplied, so 3 to the 4 to the 4 to the 4, okay, plus 4 times, now this is 5 6 minus 1. Oh, this is this, wait, it is 4 to the 5 minus 1. So I should write this as 4 to the this I should write as this one. This let me write again for your benefit. So this is 3 to the 4 to the 4 and whole to the 4, and this is 4 times 4 to the 5 to the 6 minus 1, right, this one. So this is a to the 4, that's leave it, plus 4 and b to the 4, right, we want still b to the 4, we want. So what we can do, if you want b to the 4, then we have to make some choices. So what can it be? We have already got this one, 4 to the 5 6 minus 1. So see, 5 6 minus 1, 5 to the 6 minus 1 by 4. See, this is integer, right, because we know that a minus b, we know that a minus b divides a to the n minus b to the n, right, this we define. So we can take advantage of that fact again. So we can write 4 to the power 5 to the 6 minus 1 by 4 and whole to the 4. That is nice for now. We have got pretty straightforward. We did not waste a 2. We did not write 2. We just wrote 5 to 6 minus 1 upon 4 integer. So it is a to the 4 and plus 4 times b to the 4. I get my b as 4 to the power. I get my b as 4 to the 5 6 minus 1 by 4. So this is 1. So this I got as b. Now after that, can someone suggest same approach, because we'll of course get that one. Again, product of two integers greater than, right? It is kind of same language that they also said, each of which they are saying yes, two integers greater than 10 to the 2009. That's what they are saying. So let me write this as again this one. This is a squared whole squared plus 2b squared squared. In formal proof, we have to write these lines, right? We can skip now because we already have done, but you write formally, then please write all the steps, or you can prove this as a lemma and then we can write, but then we have to write. So a squared plus 2ab plus 2b squared, this you can write directly also till here, 2ab plus 2b squared, this we wrote. Now 125 squared, yes, that is all right, that we can write 5 cube squared, 125 squared. So that of course we have to do for calculation, we have to do that. So this is, we are writing now this as a plus b whole squared and plus b squared and time a minus b squared plus b squared, we can write like that. We don't know that what happened really, but then it happens sometimes that good questions really travel, right? That's a thing, amazing thing about it. And ultimately a good problem is like a good joke, it is said in maths, so it travels far and wide, right? A good problem is like a good joke, it travels far and wide. So I mean that one culture can get inspired from other culture, and there is nothing wrong in it, right? So we whenever in maths we love the beauty, right? So once something is there, then people of course get inspired. Now this is b squared, like that, b squared, this one. So this is we observe this is a smaller factor, and if you can prove this is greater than this, then we are done. So let me now take this one. So let me turn the page now. So 4 to the power, so 4 to the 5 to the 6 minus 1 by 4 and plus 1, not plus 1, that's just that, because there is no plus 1 here. Now this is my b. So I know that if I prove this is all positive, this is positive, non-negative, I say rather non-negative, non-negative. If I can prove that larger value this exceeds, then my work is done, right? So 4 to the 5 6 minus 1. Now it's time to calculate. So 5 cube is 125, and you know that 125 and times 125 I can write very easily that if you don't know the technique, it is 25 and 12 into 13. Means if you have got some numbers ending in 5, n5 and n5, you can write 25, and this is nn plus 1, just attach in the beginning, append in the beginning nn plus 1. That is a good trick. Like for example, it happens for 15, 15. So 25 and 1 times 2 is 2, right? If you want 45, 45, then 25 and 4 times 5, that is 20. So you can keep writing like this. Okay, okay, correct only. So 4 to the 5, 6 minus 1 by 4. So it is 156, 15624, and you have to divide this by 4. So we'll get 3, 0 and 6. You will get like this. Just check this work. So you will get 4 to the 3906. And your job is, and so I can write this as 2 to the power. I can write this as 2 to the power 7812, this one, and I have to compare it with, let's see what compare with. Compare with 10 to the 2009. No, yes, 10 to the 2009. So we have to prove for the last that 2 to the 7812, this exceeds, this is to be proven, that you have to prove that this is 10 to the 2009. So you have to prove that this is 10 to the 2009. So one approach favored is that we can have many such approaches, but then maybe we can use power of 2 and 5. So this is equivalent to proving that 2 to the 7812, and this is 2 to the 2009, and 5 to the 2009. So you can take 2 here. You can take 2 here. That might be nice. That might be nice, right? So you will, that also is correct. That 2 to the 4036 and 16 to the 1009. Yes, that is small and that does the work. But if it is bound is crude also, I'll get like this, that 2 to the 2019. So this is, I can subtract this. So 03, and then I can write 68, this is 76 7603, and this is 5803, and then 5 to the 2009. So you can compare powers of 2 and 5. So maybe this may be better, that not better, this may be that one of the way that it is like you can write 2, 5 and 5 squared. It is still a good, or as one viewer told, that also is nice, as mathematically yours, a viewer suggested, it is good that anything, it is quite small bound, so anything works fine. So let me write for the benefit of all. 2 to the 15624, this exceeds 2 to the 4036, quite small bound, 2 to the 4036, and then let me check if this is correct, and 16 to the 1009. No, but it was not 1009, it was 2009. It was 2009. Mathematically yours, you said something, this one. So not, it is 2009. So you need to rework, right? So I mean that of course you can do it, right? But that's 2009. So it is not as crude, but still you can, it can be done. I mean that we have wasted so much of power here, so we can use that power and we can get. So this is not, you have to prove 2009. So better you use 2 and 5, maybe this one, and then you can use this bound, or anything you can do, it's all right. Everything is fine. So see, this problem was Romanian Maths Olympiad 2009, if you say. That was INMO 2000, not INMO, RMO. Again, both are R. Both are R only, that's a good coincidence. Both are R. One R stands from regional, and one for Romanian, right? Yes, mathematically yours is not correct because it is 1009, not, it was 2009. So anyway, it is a pretty small bound. So I trust all of you can do it. All of you can do it, I'm sure about it, because already we have covered one RMO, regional Maths Olympiad problem. So I mean, you are all now veteran in this sense, and you can of course do it. Okay, so that's all right. You can find some suitable bound. So let me compare that. See, these things get people interested, right? So see, this is testimony that both countries, 2 separate countries, but maths is same, of course. And so here it came that this is. So of course it can be done, not a problem. Okay. So have good luck with these problems. I hope you enjoyed the session, and keep commenting in the chat box, and do write your suggestion, anything that you like to be done, that because YouTube will have two sessions every week, maybe, or maybe weekly some sessions. So I mean that viewers can write that what they would like me to do, so that I can attend to their needs. That also is one small suggestion. So do write, share the thing, hit the like button, and subscribe. Tell other people also, so that they all can get motivated. After all, maths is like sharing, and we'll keep having more fun. So till then.